you want to draw it up on the board?
No. I could try.
I just turned the camera on, so that's up to you. If
I was going to say, I'm missing like my oxygen and one of the hydroxides is not visible. Or one of the OHs is not.
there you go. I like that catch. Not really a, I don't know. Actually, there's kind of a debate on whether it's called a hydroxyl group or not. I don't like to call it a hydroxyl because that makes it sound like it's an alcohol.
Yeah, does it react? So it's not specified that it reacts to the water.
I like to call it a carboxyl instead of hydroxyl.
That makes sense.
But some people refer to the entire carboxylic acid group as the carboxyl. So it's just kind of limitations on who agrees on what terminology. What three?
Did you get those at Dice?
No, I actually order these from Jet Pens, not sponsored. But if they wanted to sponsor me, man, they're very cheap. It's like $1.50 per refill, and they come so fast. But they are Japanese. They're Japanese. I've seen versions of this that have English written on them, but these ones are in Japanese.
They make the best stationery.
So how do you know which color is which?
Yeah, right. It's really, if I were colorblind, that would be harder. What three groups are attached to the front carbon? You don't have to tell me their order, but tell me what three groups are attached. OH, methyl, hydrogen. Now, which order do those three groups go in on the front carbon? Chloe, you got it?
No.
Oh.
Well, I think the methyl would be on the bottom, according to the Newman projection, right?
Good.
The one in the front, and I almost said caudal, but that's...
I'm not sure what that means. But here's our front carbon with the methyl, the OH, and the hydrogen. And when you take that perspective, the methyl group, would you guys agree that this methyl group is physically pointing down?
Yeah.
So in a Newman projection, it should be physically pointing down. Does it mean the OH is on the left?
It's coming towards us, so whatever way is towards us. So if it's this way, it would be right.
Yeah, think about this. Grab the OH, it's out here. Grab the H, it's back here. Do you agree OH is closer to you and H is further away? And then just pin it down. Elvira, which hand was my OH? Okay, we'll do it again. Here's my OH. Here's my H. OH on the right. I have never seen a student do that on an exam yet, despite saying that every semester.
Why does OH have to be your right hand? Why can't it be your left hand? Can you go the other way?
Okay, yeah. OH, H. Well, because I want this to be the front carbon, then I'd need to come backwards like this.
It's just because we want it that way?
It's because I told you, put your perspective here.
Okay.
Yes. If I had told you to put your perspective here, well, first of all, this Newman projection wouldn't work. Because now this front carbon, it is a carbon, that's a carbon. Now this front carbon has a group going straight up. Not the front carbon having a group going straight down. Do you agree that this group is physically pointing up? So it should be pointed up on a Newman projection. Here it's pointing up on a Newman projection. So the orientation of the Newman projection is not a guess. It's a physical representation of this structure.
Did you base it all off the carbon?
Which carbon?
Just in general, like do we start with the carbon?
Yeah, the Newman projection is always pointing down a carbon-carbon bond. Michael.
So that amino, or the amine group
Yeah.
that you didn't list there, is that just because we're taking it from this perspective that it's not visible?
Well, no, I'm not done yet. NH is coming out, H is coming out, and I'm putting this backwards. NH is on the right. Do you remember we had this conversation about cis and trans?
Yeah.
And these look cis to each other. We can't use that terminology, cis or trans, on a linear chain, but they look cis, and they're on the same side. So for now, when we rotate, we'll see that it's not actually cis or trans. They are both. And then the H.
Can you, like, you can't call, I understand you can't call the whole thing cis or trans, but if you're looking at it from one perspective in
Sure.
your brain, can you?
Sure, so we could say, draw the conformation where OH and NH are cis to each other.
And then that would be that.
Yeah, that would be like, that would be a good way to leverage the terminology that we have.
Yeah.
But it wouldn't technically be appropriate use of the terminology. All right, can I give you guys these models again? Would that help you in making these rotations? Okay, raise your hand if you do want one. You're welcome. And I'm sorry, they won't necessarily be the same ones. Can you guys split?
Yes.
You don't get one. You said no. Sorry? You were kidding that you don't want one.
Yeah, I was joking.
You do want one. Okay, okay. All right.
I was gonna ask, like, on an exam, like on our first exam, if there's Newman projections, things like that, will you bring these?
I absolutely will not bring these.
O and the OH.
But you are allowed to bring these. You're welcome. Are you guys able to split?
Yeah, we can check.
Okay. So if you have a model kit and you want to bring it into an exam, you're more than welcome to. But I won't have these models for you at the exam. That's crazy. Well, I hardly even have enough for all of you right now. How am I going to give, and this isn't even the whole class.
We can collaborate on the exam.
on my, okay, and that brings up an interesting point, which is I saw, I think it was a high school classroom once. The teacher gave out an exam and gave them 5 minutes to converse. And then they had to take their exams individually. And I wonder how you would approach that opportunity. Would you immediately go to the problems you know are going to be the hardest and try to brainstorm together how you'll approach them? Or would you just try and get through as many multiple choice questions as you could in those 5 minutes before you broke up? I've decided never to do it because I don't think it's a good use of my time or yours. But it's an interesting thing I think about a lot. How would you tackle that opportunity?
You definitely go to the hardest.
Yeah, and just,
Well, you break up into smaller groups first to then delegate what problems are more important. And then in the last few minutes, last like 2 minutes, you then get together in a group and share the ideas.
okay,
That's,
If you really wanted to find out, we could try it. Yeah.
I know. All right, so that's our first Newman projection. Now what I want you guys to do with the Newman projections or with the molecules you have in your hand, I want you to try and orient it so that it models what you have up there. You've got this 2-carbon chain that we're looking down. And I mean, it's longer than a 2-carbon chain, but we're looking down this 2-carbon bond. And now what I want you to do is move up to the right. So in order to do that, I'm going to keep the front carbon in exactly the same spot. And I'm going to rotate the back carbon either clockwise or counterclockwise. It does not matter which way you go, but be consistent. I'm going to move it clockwise. Back carbon, clockwise. Now I've got what type of conformation? Eclipsed. By moving 60 degrees, I have moved from a staggered to eclipsed conformation. High energy or low energy? High energy, always. Eclipsed is always higher than staggered, no matter what, because
the bonds are closest to each other.
eclipsed electron pairs, torsional strain. Remember those magnets? I've got those magnets again. If you want to feel that torsional strain again, you want to feel those electron pairs repelling, this is a transient conformation. It never gets stuck here. Just like you could never really keep those magnets perfectly aligned, they were always slipping one way or the other. This is just a transient rotation as it's twisting around a bond with some of its kinetic energy. Now I want you to take these groups and transition them into that new conformation. Use the model you have in front of you to try and keep track of what groups are where. Front carbon isn't moving, which means it's really easy to just map all of those groups from the front carbon. Do you know what I'm going to do? And tell me if this actually works for you or not. I'm going to do these in different colors. Does that look okay?
Yeah.
Would it be better if the entire projection had those different colors? Let's see it. I don't know. That looks a little.
That looks good.
Yeah?
Good, yeah.
Okay.
Really pops out at you.
Okay. Okay, did we all agree to rotate the same direction? You guys took the back carbon and you rotated clockwise?
I went counterclockwise.
All right. You went counterclockwise? Everybody went counterclockwise?
Well, because.
Okay. All right, well, do this at your own risk then. I'm gonna model these as if we were rotating the back carbon clockwise. Your conformations will all be the same as mine, but just backwards. They'll come last. So I'm gonna rotate the back carbon to the right, which means my CO2H is eclipsed with my OH, my NH2 is eclipsed with my CH3, and my H is eclipsed with my H. I'm sorry, I want to go back to the first one. Because the first one was staggered, we have 0 torsional strain. But does that mean we have 0 strain at all?
No.
We have gauche staggered strain, steric strain. Gauche steric strain. Remember what gauche meant? Like sitting in the middle of 2 people on the airplane, really uncomfortable, kind of squished, but not like really fighting for space. Where do I have gauche strain here? Name the 2 groups that there is strain between. Yes, carboxylic acid and the alcohol. The amine and the methyl.
So all 4 of those guys are.
There's
Are
more.
the OH and the NH2 okay together?
The H's don't fight for space. They're so small. So the alcohol and the NH2 also fight for space. Non-hydrogen groups. The hydrogen doesn't fight with the carboxylic acid. The hydrogen doesn't fight with the methyl. The hydrogens don't fight with themselves because they're tiny. It's literally a proton. So their electron cloud is very small, and they don't fight for space, but all of these groups are fighting. Do I have any, so again, this was steric strain. Do I have any steric strain in this eclipse conformation?
Yes.
Where, Michael?
Actually, the only one that you could see would be weak, but it would be COOH and methyl.
I don't see the carboxylic acid and the methyl group having steric strain.
It wouldn't be the alcohol and then the CO2H, right?
The alcohol and the carboxylic acid are stacked right on top of each other, so they are fighting for space. The electron pairs are torsional strain. The groups are steric strain. This conformation has both torsional and steric strain. But it's not gauche steric strain. This isn't bumping elbows with someone on the airplane. This is sitting on someone's lap on the bus. Double awkward, right? This is not gauche. This is weird, uncomfy. You're going to jump off of that seat because it's not a seat, it's a person. Where else is there steric strain? The amine and the methyl. This is also steric. So I'm not labeling the torsional strain. Why? Because it's always there in those eclipsed conformations, and it's just going to get a lot to draw out. Is that fair? All right, let's rotate one more time. I'm going to keep the front carbon the same, I'm going to rotate the back carbon another 60 degrees. Why am I keeping the front carbon the same? Just because I want to. What type of strain do I have? Where do I have? I have no torsional strain. Who said that? I don't know. Just kidding. You don't have to tell me. No torsional strain, if somebody did say that. Because there's no eclipsed bonding pairs. But I still have gauche steric strain. Where do I have gauche strain? Name the two groups. Amine and methyl.
It's not all four again?
Name them then.
Hydroxyl and carboxyl.
Yep, the alcohol and the carboxylic acid.
And then
The methyl and the carboxylic acid. So 3 sets once again. Okay, rotate it again. Now I want you guys to just start filling them in as you go, and I'm gonna draw the rest of these up for now. That was it, right? 3 on the bottom, 3 on the top. Okay. My back group now has carboxylic acid on the bottom, hydrogen on the top right, amine on the top left. My front group stays all the same. Is it obvious to you the difference between the conformations when they're drawn like this, when they're given to you like that? You can see that the eclipse is not perfectly eclipsed because otherwise you wouldn't be able to draw anything in. But you can tell the staggered is nice, clean triangles. Great. Oops. What are you thinking, Elvira?
I'm confused about what's happening in that first one. No, sorry, first on the new board. Next.
Yeah. So I'm rotating 60 degrees.
Right.
So my methyl, or my amine goes to the top left. My carboxylic acid comes straight down.
Should the CH3 be on the other side of the CO2H?
Those are eclipsed with each other.
Yeah, but like
So-
eclipsed on the other side?
They're eclipsed. You shouldn't actually see the
So it
CO2H.
doesn't matter?
Yeah, do you remember when we were talking about that with the wedge and the dashes?
Yeah.
And it doesn't matter if your wedge or dash goes left or right?
Okay. So there's no specific reason your green one isn't straight?
Correct.
Okay.
Correct. There's no reason other than it's just a little challenging to draw. They're eclipsed. What's more important is the methyl on the front carbon?
Right.
And it is. Is the carboxylic acid on the back carbon? And it is. That's a good question.
Because our little thing in Bob is the opposite.
I appreciate that.
I wasn't sure.
It's just, yeah. Okay, can we identify the rest of the strain? Do I have steric strain in this new eclipsed conformation? Andrew?
This methyl and the carboxyl acid.
And that's it. That's the only steric strain. Because hydrogens don't fight for space. So the hydrogen and the amine, the hydrogen and the alcohol are not fighting.
But it would also be torsional strength in that area because it's eclipsed.
Always torsional strain. Yep. Which is why I physically drew the eclipse conformations higher. I want you to think of those as being highest in energy. What about my next one? Do I have steric strain? Where?
Between the carboxylic acid, the methyl, and the amino, and the alcohol.
Good. Amine and alcohol, methyl and carboxylic acid. Ooh, that's fewer strain than our other two eclipsed conformations. All right, last one.
It would just be the torsional and steric strain between the alcohol and the amine.
More torsional strain, and then the alcohol and the amine.
Hydrogen, does that produce torsional strain as well, or no?
Groups don't produce torsional strain.
Not alcohol, I meant the hydrogens.
Hydrogens as a group, methyls as a group, any group doesn't make torsional strain. It's the bonding pairs of electrons that make torsional strain. Torsional strain comes because these electron pairs are in front of each other, regardless of what the group is, which is why torsional strain is always present to the same amount. Torsional strain never changes. And it's that example with the magnets. It doesn't matter what's on the other side of those magnets, but as those magnets eclipse with each other, they repel and they push each other past.
So, for like that bottom one right there, are there like just 2 areas of steric strain?
Yep.
So there's just...
So this has 3 steric strains, 2, 3 steric strains, 1, 2 steric strains, 1. And there are different types of steric. Yeah, this is eclipsed steric, and this is staggered gauche steric.
I think I'm confused how we know like that it's torsional and steric.
What causes torsional strain? First of all, what is torsion supposed to make you think of? Testicles. Oh. Torsional is supposed to make you think of twisting.
Okay.
And what happens when you twist? The electron pairs eclipse with each other. And as those electron pairs, which are little magnets, come by each other, they push each other away.
Okay.
So anytime it's eclipsed, torsional. We don't have to say it, but we can. Torsional, torsional, torsional. And it doesn't matter what's on the other end of the groups. The simplest molecule, ethane, CH3CH3, has torsional strain when its bonding groups are eclipsed. Steric strain depends on what the groups are. And you can visualize this with your models. Put these at an eclipsed perspective, and these groups that are gauche to each other are physically fighting for space in the middle. Because remember, molecules are not stagnant. These are wiggly, spinning, vibrating guys. So when they're next to each other, they're fighting. And when they're opposite from each other, there's no fight. So we call this an anti-configuration. Notice that that is the zigzag from a Newman projection. It looks like the 2 biggest groups are anti. And that means no steric strain. Why do we draw a bond line as zigzags? It's the lowest energy conformation. It gives us the least amount of steric strain. As soon as those groups come gauche to each other, they start fighting for space. And when they're eclipsed with each other, they fight for space. So steric strain, non-hydrogen groups. Torsional strain, always in the eclipsed conformation.
Okay, so in that other eclipse diagram on the first board,
Yep.
so the 2 steric strains are separate from each other. It's not 2 because they have the steric strain.
Yeah, this is methyl sitting on top of the amine, and this is alcohol sitting on top of the carboxylic acid. As opposed to 60 degrees before that, it was alcohol and carboxylic acid bumping elbows.
Okay.
And the alcohol bumping elbows with the amine, and the amine bumping elbows with the methyl group.
Okay.
Now they're sitting on top of each other, more isolated.
Is the one with the 4 groups of steric strain still preferred over the eclipse version, even though there's less steric strain in the eclipse version?
There is no conformation that has 4 strains.
Like your
3,
where all 4 groups are bumping up against each other.
Yeah.
Is that still preferred energy-wise over the one with torsion
yes,
and steric, but less steric?
yes.
Okay.
Torsion will always increase. So I want you guys to recognize that the top 3 are eclipsed are the highest 3 conformations. So what I want to do right now is rank them. I want to rank these by their energy. So let's rank the top 3 since those have the same amount of energy. Or sorry, since those all have torsional strain. The 3 highest energy conformations. First highest energy is over here on the left. Highest energy. Why? Torsional strain and 2 steric strains. Torsional plus 2 sterics. Are the other 2 eclipsed conformation equal to each other? They both have torsional strain, and they both have 1 eclipsed set of groups. Steric strain increases with increasing size. Do you guys remember what steric means, right? Stereo, spatial, space. Sterics is referring to size. The bigger the group, the more space it takes up. The more space it takes up, the more fight for space it's going to have. So these have the same amount of steric strains, or the same number of strains, but one of them involves larger groups. Good. Carboxylic acid and the methyl is our second highest energy, and that has torsional plus 1 steric strain, but that steric strain is bigger. Our third highest energy has torsional strain and 1 steric strain, but that 1 steric strain is smaller. All right, now there are quantitative numbers that you can actually put on these, and we're not going to get that in depth. So in general, I want you to consider a methyl group, an alcohol, and a halogen as all being roughly equivalent. The biggest group that you generally will run into, the one with the most steric strain, is the tert-butyl group. This is just the most common introduction that you'll see in OChem 1 and generally in OChem 2. The tert-butyl group possesses a lot more steric strain. We call it bulky. It's got 3 methyls all joined at 1 central carbon. It takes up a big amount of space. So you can consider most other things equivalent in size, roughly, equivalent in their steric strain, but a tert-butyl group definitely the biggest. Or just in general, increasing number of atoms, more sterics. Seems reasonable, right? The more atoms you have, the more space you have to take up, the more steric strain that you'll have. Let's rank our bottom 3. Which is our lowest energy conformation?
Probably the last one.
Why?
Because it only has 2 sources of steric strain, 3 unrelated.
Exactly. 3 steric strains, 3 steric strains, 2 steric strains. So this is 6th highest energy, or the first lowest energy. That's another confusing part about these ranking problems. You need to pay attention to whether you're being asked to rank in order of stability or in order of energy. Are you going by increasing energy, or are you going by increasing stability?
So that's the most stable.
This is the most stable. Yep. Most stable, lowest energy. What about 4 and 5?
The one that takes up more space. Like methyl. How many times the methyl interactions is that a good basis?
Right.
The one where the methyl and the
The one in the middle
carboxyl
is the.
are against each other, would that create more steric strain because they're both larger?
Good.
So that one that's in the middle would actually be the fourth highest, and the fifth highest would be the one in the middle.
Right. I'm going to say the carboxylic acid is the one to look out for here. It's the largest group. It's got the most atoms going on. I hear you when you say that it doesn't have the most atoms. Relative to the methyl group, it has the same number of atoms. But it actually has a longer bonding system. All 3 of the hydrogens are bonded to carbon, whereas the hydrogen is actually carbon, oxygen, hydrogen. So it is the longest structure. So the carboxylic acid having 1 steric interaction versus the carboxylic acid having 2 steric interactions.
Is it just number of atoms, or would you also take into account the size of the atoms? Like oxygen's bigger than carbon.
Actually, oxygen is not bigger than carbon.
Then atomic
Because
mass.
it's more electronegative, so it's actually smaller.
We say that it has a higher effective nuclear charge. Carbon and oxygen have electrons in the same orbital. So the electrons are essentially the same distance apart, same distance away from the nucleus. But oxygen has more positive charge in the nucleus, so it's able to pull on those electrons more strongly. So oxygen has a stronger effective nuclear charge, which shrinks its atom size. So it's not so much about the size of the nucleus, because oxygen does have a larger nuclear size, but the size of an atom is not about the nucleus. The nucleus is 1/1,000,000th of the size of the atom. The atom is about the electrons. But no, in general, I mean, we can really think of these in the same period. These are pretty much equivalent to each other. Yeah.
If you had like an iodine in there, that would be significantly bigger.
Correct. Especially if we compared a chlorine to an iodine, we can say that the iodine is going to be a bigger group than the chlorine. But when we compare these atoms, I will say this is kind of a challenging one because it's a little bit hard to balance what's the bigger group. And maybe because of that, I should have given a better example. But in general, I give questions where you won't have to wrestle with that. It's going to be obvious. Count the number of strains that it has, and it will be obvious which group is bigger, which group is smaller. Gavin?
Atomic radius?
We are not talking about atomic radius as much as we're talking about just group size.
Oh, well, like electron clouds and stuff?
Kind of. Yeah, and I want you to think of these. These have different steric interactions, but they are close enough to each other relative to the tert-butyl group, and that's going to be one of the more common groups you see. But there's no amino acid that has a tert-butyl, so. All right, why don't you guys take 5 minutes, work together, and rank the 4 Newman projections that you see below. Here's how I want you to rank them. Number 1 is the most stable. Please write that down so you don't forget it. Number 4 is the least stable, which means I'm asking you to rank them opposite of how we just ranked them. We just ranked them as 1 being the highest energy and 6 being the lowest energy. Fair? I want you to be able to recognize the difference between those ranking perspectives. Good. Number 1 is your lowest energy.
I know, I'm like, pretty sure this is connected to
Because the big groups are
Oh,
all
yeah, because I already got confused because I thought it was eclipse. It's not. No.
Well, our second one is gonna be, our second staggered one is gonna be our number 2. And then our number 3 is gonna be the third one, and the fourth is the first one. Third one.
No, I was thinking,
I agree.
I thought you ranked this one as number 1. And I was like, no way.
Wait, how did you guys just?
Actually, I feel like I'm misreading something.
Number 1.
Like how the bottom two that are large.
I don't know. My brain is just not
This is the largest part.
Thank you.
the largest part of the structure.
Largest part of the structure.
Yep.
Here creates a
And
larger
the big one, our number 3, the big one, doesn't matter.
Yep.
That's why.
So here it's,
As most energetic.
yeah, this would have to be lower.
Yeah, because this is also in the staggered. But these two are eclipsed, which means they're automatically of higher energy.
So I think this is lower energy than this
Oh, that you think these are switched?
because your carboxylic acid in front interacts with the OH on both of them, and then it interacts with a smaller group or a larger group.
So,
Do you agree?
so you're going off the carboxylic acid, but
No,
wouldn't
that's
this
nicer than what we got.
section be representative of a larger?
Had like
Strain.
Oh, I see what you're saying. So this is the most
Stable.
least energy, most
Mhm.
stable.
Yep.
Okay, that makes sense. So if that's the case, then yes, if you want to,
but it's like our merch.
Good.
that makes sense.
Good. Oh, I'm sorry. Your structures are a little hard to read, aren't they? The one on the right. If you finished, try translating one of these Newman projections into bond line. See if you can draw the bond line structure of what you have. It looks good. Yep. Take it out of Newman. Looks good.
We're struggling.
Really?
We're just struggling with numbers.
Yeah, we're struggling articulating our thoughts
Okay.
to one another.
Yeah.
But you all agree on the order?
On the jumble of thoughts.
The words are just hard.
It's just when you try to be like, the fourth one is the second one is the number 2. The second example.
Yeah, actually, I think what I could have done better was put letters with these A, B, C, D.
But here we are. Instead we struggle.
Okay, why is this 4? Why is,
I agree with these,
I've already drank.
why is D?
but I disagree about these.
Why is D more stable than B?
I agree.
Well, we have to be
I agree.
Yeah, they were just like yelling at us and telling us like all that we were doing wrong, and they're like, so for that reason.
Doing great.
next it
On this one,
today, at the nursery station,
steric strain is
one chair for the
never gauche. It's only eclipsed. So like OH is eclipsed with H,
blah,
and so it doesn't have any steric strain. But here, the carboxylic acid and the large group are eclipsed. You bet.
Okay, so I'm
Mm-hmm.
thinking this is dash, but I'm not sure I'm right.
There's 12 people there.
What is H?
My CO2H.
So which one are you drawing as your back carbon?
I'm drawing this is my front carbon.
Okay. So CO2H should be, at the group pointing down.
One what?
You're saying this
That guy.
front carbon is this,
Yeah.
and CO2H is coming off of it, so there's your CO2H.
Oh, right here.
When you're done ranking, try to draw them into bond line.
Well, I almost did one of those.
But it is easy to do.
They are making it so that we have to do the night shift, not as morning vibe, for the morning mess, but then that wakes people up, and if you have like this restlessness trying to get out of them, because, you know, you just have to get the vitals, and then you have to get everybody else's vitals.
That doesn't necessarily go to a cause.
Central interval, is that what you're saying?
You know that
But they
like
were
that
basically like,
counts as
well,
that the end should be something,
you know,
as opposed to just they don't.
yeah, they literally were like, get them up last, which makes sense, but then the nurses were like, but unless they're on heart meds, because if they're on like blood pressure meds or like something like that, then you need to get them first. And I was like, but what if one of the residents is a fall risk, but also has a heart med, what are we supposed to do? And they're like,
Okay, you guys ready?
I don't know.
What was the first thing you did when ranking these? So I heard two things. One, identify all the steric strains. Andrew added to that and said, separate torsional from non-torsional. Yep, separate your eclipsed and your staggered because?
Staggered is lowest energy.
Right, staggered will always be the lowest energy, eclipsed will always be the highest energy. So you have just split it in half. If this is a multiple choice problem and you're given the order of ranking to choose, you have already narrowed down a lot of the options to the ones that have the highest and lowest energy in the right spot. Then you looked for the number of steric interactions, and did that help? Did identifying the difference in the steric interactions do anything for you?
Not entirely by itself.
The two highest energy each have one steric interaction. The two lowest interactions, or the two lowest energy, both have two steric interactions. So drawing it out didn't really, or identifying how many strains didn't help as much. So we have to dig into the difference between the strains, the difference in the sizes. So when comparing those two highest energy groups, I'm going to shorthand this. I'm going to redraw everything, or I'm going to only draw, the groups that are changing. So I've got this group versus in my other highest energy, I've got CO2H against CO2H. You see how we just ignore everything else and pay attention to what's changing? Steric interaction with a bigger group, steric interaction with a smaller group. So my highest energy had that larger group, and my second highest energy had a smaller group. Because the carboxylic acid at the bottom never changed. What it only changed was what it was eclipsed with. And then we do the same thing in our last two. We can ignore everything else. And we can look at what the carboxylic acid at the bottom is eclipsed with, staggered next to, gauche to. This time, notice how the carboxylic acid has an interaction with the alcohol in both conformations. That's not changing. That's the same between them, which means I'm looking at this steric interaction between a big group and this steric interaction with a smaller group. They have similarities and they have differences, and the difference is what I have to lean into. Here's my lowest energy. Here's my second lowest energy. Okay, good stuff. This molecule is citric acid. So I took that last structure on the left and I drew it as a bond line form. What I didn't do, though, was add stereochemistry, and I'm going to do that now. If I take that carboxylic acid and that alcohol as they are, the alcohol is going to be pointing away from me, and the carboxylic acid will be coming forward. And I want you to notice how my biggest groups, the carboxylic acid, and then this 2-carbon chain, methylene and carboxylic acid, these are anti to each other. They're directly across, and they create that zigzag bond line structure. But if I look at the first Newman projection, the eclipsed Newman projection, and if I translate this into bond line, I want you to notice how I'm mapping my carbons as well. I kind of forgot to put the map in here, but I'm numbering them from the Newman projection, and then I'm placing them into my bond line structure. Here, I'm going to have a zig-zig in my structure instead of a zigzag. I've taken this and I've laid it down this way, which means I've got OH. What have I done? Yeah, OH back, carboxylic acid forward. Here's my 1, 2, 3, 4, 5. You see the zig-zag right here? I don't have a zigzag structure anymore. I have a zig-zig structure. Those high energy conformations, those eclipsed conformations, they always give us that zig-zag bond line. Those low energy conformations give us that zigzag bond line. That's why organic chemistry is known for its zigzags. It's because that is representative of what the molecule looks like most of the time at its lowest energy. All right. 2 types of strains that we've looked at so far. Can you name them? Steric strain, torsional strain. Steric strain is what? Can you define it? Groups competing for space. Torsional strain is what? Okay, I'm going to say not electron clouds because steric strain is actually more like electron clouds. Groups competing for space. Electron repulsion.
Yeah, from eclipse bonding.
Bonding electrons. Bonding electrons repelling. That's torsional strain. Bonding electrons repelling. There's another type of strain, and this appears in rings. We get angle strain. The tetrahedral carbon wants to be 109 degrees. But inside of these small rings, we get bond angles of much less than 109 degrees. Until we reach the octagon. Nope. Hexagon. I know my shapes. Like the UFC? What's that? Oh, no. Not like in the UFC. The hexagon actually gets pretty close to 109 degrees. The pentagon is not far off, but the hexagon is very close. And so the hexagon becomes a very common cyclic shape in our organic world because it minimizes steric strain. Minimizes angle strain. Whereas cyclopropane experiences maximum angle strain. And in these diagrams, we're not actually going to do that much with them. You can kind of see a side-on perspective of these groups. You can see the tetrahedral carbons, all 4 bonds coming off of each position. And you can see how the smaller rings, they try to twist and bend, and they don't look planar the way that we draw them. They look all twisted out of shape. We're going to look at one of these shapes the most. Cyclobutane kind of takes this little bowl conformation. It tries to push 2 of its groups up and 2 of its groups down to try and get rid of eclipsed bonding pairs. Cyclopentane takes on what is called an envelope conformation. That's why it looks a little bit flat and then twisted up on just one side. But cyclohexane takes on the chair conformation. So at the bottom, we're going to look at cyclohexane's chair conformations. First, I think it's best to just start with a substituted cyclohexane. When I say me, what am I saying? Methyl. So is it legal for me to say CH3 on the paper but methyl on the board? And did I have to draw anything at all? No, I could have just left it as a blank line, and that has to be assumed as a methyl group. All right, well, I guess before we get into that, here's an example of a cyclohexane in its chair conformation. I generally like to project on the screen this website that shows the 3-dimensional conformation of cyclohexane, but my computer has been really finicky with the recordings, and I'm not sure if it's going to crash it or not. This is our cyclohexane. What I want you to try and notice is that there are 2 sets of 3 carbons. 3 of these carbons sit up higher than the other 3. I like to call those up carbons. And 3 of these carbons sit down lower than the other 3, and I call those down carbons. And you can actually see the up carbons because they have a blue group that points straight up. And you can see the down carbons because they have a blue group that points straight down. So in the chair conformation, we have 2 groups. Now I've given you the template of a chair. I have, over the years, moved away from having you guys draw chairs and grading them because they can be challenging to draw and they don't usually end up very well. But I am still going to try and demonstrate it for you, and I'd like you guys to try and copy it. We start with 2 horizontal lines, 2 diagonal lines, but they should offset from each other. So, sorry? They're parallel, but diagonal and offset. So don't make these flat, make them diagonal. And I want you to notice how they're offset. Whichever one is on the bottom lags behind. We don't have to draw it up and to the right either. We can draw it up and to the left, but notice the one on the bottom lags behind. Or if you were to draw these dotted lines, you should always make this little square within the 2 lines. Then we draw 2 V's connecting these parallel lines. On the down side, you draw an up V. See how that kind of looks like a V, but it's upside down? And on the up side, you connect them with a down V. And you get the chair conformation. Now, in my opinion, they should have called it the bolt conformation, like the lightning bolt It looks a lot like a lightning bolt, although I think you can kind of see like the lazy boy chair. It's hard. I don't like it very much, but we call it the chair conformation. Now on the other side, up, side, down, V, down, side, up, V. These drawings are identical to me, but actually Active sees them as different things. And when Active gives you a problem with one, it wants you to draw the chair conformation with the other. But to me, you can use either one to communicate anything. So, but again, you're not going to be drawing a lot of them on exams. Probably never. You just need to be able to interpret them. Do you see the up carbons and the down carbons? Look at that carbon pointing up, pointing up, pointing up, pointing up, pointing up, pointing up. Up carbons have what we call up axial groups. Relative to the ring and relative to the axis of the ring, there's a group on these up carbons that points straight up. That's what you guys saw here with my up carbon and that blue group pointing straight up. But notice that the up carbon has another group as well. That other group points more down than up. But it doesn't point straight down. It points more like equatorial to the ring. So we call it a down equatorial group. So to draw this from my up carbon, I'm not going to draw it horizontal, but I'm not going to draw it straight down. I'm going to draw this group just down a little bit at an angle. And in my opinion, that's easiest to do from any of these four corners. But from the internal carbons, drawing the equatorial groups is a little challenging. There is a trick. The bond can be parallel to either of these bonds off by their sides. So in this case, it would look a little bit like that. Notice that it's not straight down. It's still off to the side a little bit, but it is a little funky. Up equatorial, up axial, and down equatorial. And what about our down carbons?
Down axial and then up equatorial.
Perfect. 3 down carbons, down axial on each, and up equatorial on each. This is the lowest energy conformation. I want you guys to realize that this molecular model has 109-degree bond angles no matter what. It has just given us a tetrahedral carbon, and you can see how this conformation arises naturally from that structure. All right, now I want to take this bond line structure. Also, sorry, do you guys see this up above on that cyclohexane chair? All of those different groups, down carbons and up carbons, down axial, up axial, down equatorial, up equatorial. What I want to do now is take one of these groups and I want to substitute it for a methyl. So this is what we call the top-down perspective. I think you could call it like bird's eye view. If you're just looking straight down on the ring, it looks flat. looks like just a hexagon. It's not until you take the perspective of the ring on its side that you start to realize it is not flat. It is a chair. It's bent out of a plane. So we're going to take the top-down view, which just says I have a group pointing at me, and we're going to draw it from its side perspective, and we're going to say that it is pointing up. Well, there's one other thing, one other assumption. Remember, this is all about assumed perspectives. There's one other assumption here. The ring is always assumed to be closer to you on the bottom, which is why in that structure up above, you can see that the side closer to you is bolded, indicating that it's, sorry, the bottom side is bolded, indicating it's closer to you. Okay, so this methyl, would you agree that it's coming out of the board towards you? We're going to say that that is an up group. Bold, wedged, up. Dashed, away, down. Wedged is an up group. Dashed is a down group. So I want to place my group. I can place it anywhere. Doesn't matter. I prefer the four corners. I think it's easier to draw those positions there. So I'm going to say, let's draw it on the top left. I'm going to put the top left carbon as the carbon with my methyl group. What position is up on that carbon? Axial. It's an up carbon, which means it has an up axial group. So my methyl group goes straight up. Is that a resonance arrow? What is that, Liana? It can be a reaction arrow, an equilibrium arrow, which means that these two things are not equivalent to each other. They're not the same. They actually require energy to move between, whereas resonance is two or more limited depictions of the same structure. These are not depictions of the same structure. They're different conformations. What if I had not chosen to place my methyl on an up carbon? What if I had chosen to place my methyl here on this down carbon? What group is up on that carbon? I'm going to repeat it. What group is up on that carbon? And can you repeat what you said, Michael? Does that sound like not up? I'm glad you said that, because that is a very natural instinct. I placed it equatorial or axial, I'll place it axial again. But this is an up group. So whatever position it goes into the ring, it goes up. Cardi B said it well. If it's up, then it's up, then it's up, then it's stuck. And in an interview on late night, she said she was talking about constipation.
Oh, really?
Yeah, apparently. If it's an up group, it's always up. It doesn't matter what carbon it's on, it's an up group. So it's an up equatorial position here. Now again, this is my least favorite position to draw because it looks kind of funky. I'm going to convince myself that that is equatorial by confirming that this carbon has a down axial hydrogen. And I could do the same thing here by confirming that it has a down equatorial hydrogen. So I'm just adding in unnecessary hydrogens to really verify what I'm looking at. What we have just demonstrated is the chair flip. In order to do a chair flip, a chair has to first rotate into what is called a boat conformation. And you can see that the boat kind of looks like a bowl, and it has these groups pinned up against each other. And this is a high energy conformation. It has a lot of steric strain. It has some torsional strain. So this is a high energy conformation, much like our eclipsed conformations for the linear chains. So again, I started with 3 blue groups up, 3 blue groups down, and I twist into the boat, which has this kind of mixture of blue and red up and down. And then I twist into the chair. Now this makes it really hard to see because all of my groups are the same. So I'm going to swap this out now for a methyl group. I know it's not exactly a methyl group, but it's very close. There's always this alternating pattern, up, down, up, down, up, down. So if you're confused in drawing a structure, it goes up, down, up, down. There's my methyl group. What position is it in right now? Up. Axial. Now, as I flip into my boat and then flip into my other chair, what position is my methyl group in now? It's still up. Because if it's up, then it's up, then it's up, then it's stuck. It's still an up methyl group, but now it's not axial, it's up equatorial. The change is that the carbon has flipped from up to down. Here is my up carbon, and now my carbon flips into a down carbon. But the groups keep their relative position. That group is just flipping as the carbon rotates slightly. Michael?
So when you're classifying like up and down carbons, it's the carbon in the middle, not necessarily what's connected to it going off, right? Because even though it was an up carbon, it's an up equatorial and not a down equatorial.
Correct, it stays up.
Okay.
If it started up, it ends up. So during a chair flip, up carbons become down carbons. Down carbons become up carbons. But up axial groups become up equatorial groups. Down equatorial groups become down axial groups. Up carbon flips to down, down carbon flips to up. Up axial stays up, but becomes equatorial. Down equatorial stays down, but becomes down axial.
Do all of the carbons flip when you're going from one to boat to the other?
Yes. During a chair flip, every carbon switches between up and down. Every group switches between axial and equatorial. But no group ever moves from up to down. If it's up, then it's up, then it's up, then it's stuck. And if I hear some Cardi B bumping during the midterm, I'll know you're cheating. Now, what about the strain between these two conformations? I've done a challenging job of demonstrating to you that this molecule can rotate between two conformations, but which of these two conformations is the most stable conformation? Which, are they the same energy or are they different energies? The Newman projection can tell us. So I'm going to draw a Newman projection for the one on the left and a Newman projection for the chair on the right. But I want you to notice that these Newman projections are actually double Newman projections, because as you sight down one of the carbon-carbon bonds, you sight down the parallel carbon-carbon bond at the same time. So the two Newman projections are connected by this up carbon in the middle and this down carbon in the middle. And you'll see that on your Newman projection. They're connected by an up and a down carbon. So based on the Newman projection I gave you, we need to take a perspective that puts a down carbon in the middle. So I'm going to say we start with this chair conformation on the left. And to get, oops, I'm actually going to draw my perspective here. I want to see how the methyl group is interacting. So I want the methyl group in the Newman projection. Here is the bond I'm going to cite down. Here is that parallel bond that I'm going to cite down. Here is my front carbon, back carbon, back carbon. The front carbons are connected to each other by this down carbon. That's what you guys have already on your Newman projection. On the left front carbon, my methyl group is pointing straight up, and my hydrogen is down to the left. On the right front carbon, I just have hydrogens. The two back carbons are connected by this up carbon. And then the other positions are just hydrogens. Do you see any strain in the molecule? Is there torsional strain? It's a staggered Newman projection. It's a double staggered Newman projection. Rowan, could you grab the door, please? Thank you. It's a staggered Newman projection, so there's no torsional strain. But is there any gauche steric strain? We'd have to look at the methyl for sure, and we'll look at the things around the methyl. On the left is hydrogen, no competition, and on the right is a carbon, is a CH2. Methyl and the CH2, we call this 1,3 diaxial strain. But it's just a type of steric strain. And guess what? If the methyl group has that steric interaction with one up carbon, what do you think is stopping it from having it with the other up carbon as well? If we're saying that the methyl group is fighting for space here, it should be fighting for space here. We just can't see it because that other up carbon is in our Newman projection. We'd have to take a different Newman projection to see that strain. But it stands to reason, if we can see it interacting with one up carbon, it's interacting with the other up carbon as well. That's not just one steric strain, that's two steric strains. With nothing else in the molecule, an axial group has a minimum of two steric strains. Now I'm going to draw the other Newman projection for the other chair conformation, and we're going to prove that the equatorial position minimizes steric strain. I have now put my methyl carbon on the back. I'm still connected by down carbons in the front and up carbons in the back. My methyl is up equatorial. Hey, look at that, up equatorial. And I've got hydrogens everywhere else. Now I look for steric interactions. What's on the sides of the methyls? Hydrogen and hydrogen. No sterics. No steric strain.
So in order to get to that position, you have to go to the boat configuration first.
That's true.
Down, right?
Had to go to a high energy conformation to get to a lower energy conformation. We would say that looks like this exothermic energy diagram.
So I want to
Where?
Just in general,
The only thing in axial positions are hydrogens, and the methyl is in an equatorial position.
So the methyl was in an up axial, and it will go to an up equatorial. Is that how you describe it?
Yes.
Movement of the methyl?
Up axial, up equatorial.
Okay.
It was on an up carbon, then it's on a down carbon. Although you can't see that from the Newman projection.
But it's still a down carbon.
Mm-hmm.
So the carbon in the middle switches, the group stays.
Good. Carbons flip. Groups maintain their relative position, but they change their location relative to the ring.
Makes a lot more sense.
Good.
So I guess you wouldn't need to know this, but if you did need to know this, you could know that that's a down carbon because the methyl is equatorial.
You could know it's a down carbon because it's next to an up carbon.
Oh, yeah.
Or you could know it's a down carbon because it has a down axial group.
In the back.
The back carbon. The back carbon has a down axial group and an up equatorial group.
Okay.
Yeah, you can infer that.
Can you explain again why axial groups have two sterics?
Because we saw this one from the Newman projection, which means it must also have this steric interaction. Or in other words, we saw this steric interaction from the Newman projection, but what would stop it from having this steric interaction? Nothing. Those two positions are equivalent to each other.
So it's the carbon at the top of the up carbon
Yep.
there, and then it's the dot is the other one that's having the steric.
Right. But from this perspective, we can't see it.
Hard to see.
Exactly. Okay, so here's the rule about higher energy chair conformations. More axial groups, higher energy. More equatorial groups, higher stability. You guys are comfortable with the difference, the distinction between stability and energy? Good. Okay, I have a new worksheet for you that has you go through chair flips. I don't believe I put this on Canvas yet. I'm sorry. And it's scaffolded to give you less and less information as you go so that you have to work harder and harder to apply these skills as you go. Two of them there. Can someone remind me at the end of class to upload this to Canvas? Thank you. Okay, so we take this chair conformation that we're given, trans 1,2-cyclohexane diol, and we see it already put into one chair conformation. The up OH is on an up carbon, making it up axial. The down OH is on a down carbon, making it down axial. In the chair flip, the up OH stays up. The down OH stays down. But they'll flip positions from being axial and equatorial. So, in that second chair conformation, what do we draw in? Is it obvious?
Well, there's only one that's up and one that's down.
What is this position?
Equatorial is up, right? Even though it's down carbon.
Right, here's a down carbon. That's equatorial. And do you see how it's literally pointing to the top of the board, not the bottom of the board? That's up. Would you agree the top of the board is up? I think we all kind of agree to that. And here it's pointing down. I mean, it's not a great down, but it's equatorial down because it's on an up carbon. So here's my OH. Here's my OH. Wedged OH, wedged OH, wedged OH.
You don't have to draw the wedges in the chair confirmation?
We don't draw wedges or dashes. Thanks for asking that. It's assumed. We know what perspective we're drawing. Okay, now notice I have this equal sign. That's because there's more than one way to draw this chair conformation. Here, I took a perspective where my groups were on the back carbons, but if I rotated this around like a saucer, I could be looking at those OHs as if they were pointing at me instead. So these are equal to each other. Down OH, up OH. The next 2 days, we're going to be talking about absolute arrangement in space. And I want to point out how from up to down is clockwise, up to down is clockwise, up to down is clockwise, up to down is clockwise. If you were to draw a chair conformation here, where you went from up to down counterclockwise, that's a different molecule. And we're going to prove that in our next 2 lectures. But I want you to start paying attention to it now. You cannot throw these groups into the ring however you'd like. They have to maintain relative position next to each other. All right? So the time is yours to fill these chair conformations in. Notice how on the last one, you need to draw the top-down structure from its chair conformation. Once you've drawn chair conformations, circle the higher energy or circle the more stable. Figure out which one is a more stable structure, which one is a more energetic structure. Actually, let's do that for this one first. Which of these is a higher energy chair conformation? Why? Both are axial. Exactly. The more axial groups, the higher the energy. Okay. You guys have like 7 minutes.
Would those last 2 be equally stable because they're both equatorial?
Well, these are exactly the same thing.
They're exactly the same.
This is just looking at it from a different orientation. This is like saying you want to look at it from here versus looking at it from here. They're identical to each other. Yep. High energy, high stability.
Just to kind of clarify, so these are both OHs, so it doesn't really matter there, but it wouldn't matter which one you put it on, as long as from here you like keep it consistent.
Correct. Yeah.
But the initial one, it doesn't matter.
Yeah, so if you were going to start from scratch, you could have put them on any of the 6 carbons.
Even if they were a down carbon?
Correct.
Okay.
So long as you maintained that same orientation, up OH to down OH clockwise. So you could have, if you were drawing this from scratch, you could have started by drawing that.
Yeah.
And then drew the chair conformation to this.
I guess what I was more saying is like, if I were to put the turbuto here,
Mm-hmm.
like that wouldn't matter as long as from this point it's kept consistent.
Correct. Now this one is a little bit, oh, I must have clipped something. I have an O there on the second structure on the left. I think is supposed to be OCH3. Methoxy. I'm sorry about that. It's got OH on the right dash, and it should have OCH3 on the left dashed. Subscript goes on the right. Yeah, actually, it's kind of interesting, right? But the subscript is always on the right of the chemical symbol. So yeah, here it's perfectly symmetrical. So either way you had drawn it would have been the same. But on this one, it should go methoxy to hydroxy clockwise. And if you had flipped those, it would have actually been a different structure.
Okay, I see.
So because they were 1,3 and not 1,4, or because the next one you were looking at was 1,4, it didn't matter.
Okay.
Good question. You bet.
Is this right?
Yeah. Oh, no. You know how you're going methoxy to hydroxy clockwise? Methoxy to hydroxy clockwise?
So it does matter.
It does matter. They need to be flipped.
I mean, like, when you say clockwise, you mean that from chair confirmation to the next one, OH would have gone to the.
I'm saying you went methoxy to hydroxy clockwise, and now you've got methoxy to hydroxy counterclockwise. Methoxy to hydroxy. Right. And maybe that's a challenge because it was just O at first, and then I changed it to be OCH3, because O is not a thing.
Yeah. What about this third one, right? Like, thinking about it this way.
Perfect.
Butyl, and then because of that conformation change.
Yep.
This up carbon becomes a down carbon. Down carbon becomes an up carbon.
Exactly.
That's how that works. Okay.
Exactly.
But then in this example, they're both technically up carbon still, right?
Oh, I did screw up. Yeah, you're right.
So okay, so this is technically supposed to, this line here would be.
You should just
Somewhere else.
ignore the second one.
Okay.
Or redraw the groups as down axial groups, not up axial groups. Okay. Yeah, sorry about that. Thanks for pointing that out. There's not a best way to draw that one otherwise. I don't like it much. Just ignore the second one. That's my bad. Yeah. Here I am. If it's up, and it's up, then it's stuck, and then it goes from down to up. It wasn't stuck, was it? Took some prune juice or something. Laxatives. Great work. Good. How far clockwise? Mm-hmm.
So I'm trying to just visualize like the actual flip. So they're in.
So this is actually, what do you call this? This is isopropyl.
Oh, sorry, isopropyl.
What do you call this?
CHO.
Okay, aldehyde.
Aldehyde.
Yep. Good. Well, it doesn't really matter, but how you number it or keep track of it, but there's a way to keep track of it.
So this is 2, this is 3.
Good. Numbering it is great. Now make sure that 1 goes from up to down.
Oh, okay, so instead of 1 here, it would be 1 here. You'd start at.
Oh no, I meant like from 1 here, 1 here. Because the top-down view.
That's right. Up goes to down. So then this one would become number 1.
Good.
Clockwise.
The top-down view is neither chair conformation. The top-down view doesn't give us that information.
That means this up axial chlorine would become an up equatorial.
Perfect.
Okay, so that means it would be like that.
Perfect.
That makes a lot more sense.
Is that wrong?
Tert-butyl has stayed equatorial. Ethyl has stayed axial. So all you've done is just rotated this around.
Right.
You haven't flipped the chair.
Flip it into.
Yep. I erased it. If it's an up equatorial group, you've got it. Up axial becomes up equatorial. Up axial becomes up equatorial.
So like that. 1,
Yep.
2, 3, 4.
Yep.
Down axial. From well, it went from up equatorial, so it does.
I want you to look at it, not me. It goes from up equatorial to
Up equatorial to down axial. No.
if it's up, then it's up, then it's up,
So
then
it has
it's
to be up axial.
and it's on an up carbon. You drew it as down
Oh,
equatorial.
You're right. So this line would go up the opposite
Correct.
And it would be
Straight up.
axial, isopropyl.
Good.
I'm gonna redraw that.
Yes. Okay, would you rather I draw all the answers up right at the end of class and make you stick around to copy them down or grab them from the video? Or draw them at the beginning of class tomorrow as we move on?
Beginning of class.
Okay, great. I appreciate that too. That is all our time then today. You're free to go. I'm happy to answer any other questions, and we'll wrap this up tomorrow.
This becomes an up equatorial,
Mm-hmm.
and this is an up equatorial.
Yeah, but
This
any
is an up axial.
any reason why the chlorine and the aldehyde have swapped positions?
No reason.
Okay, I agree.
I don't understand chair structures, so.
Well, it's not super intuitive. If you have a model kit, build these with the model, and then work on flipping them.
So both of these, I know they're axial.
Well, no.
No?
From the top-down view, nothing is axial, nothing is equatorial.
Oh, okay.
Things are up or down.
Okay.
The top-down view only gives us up and down.
Okay.
And then we know there are two ways that it can be oriented. So you chose first, put the ethyl up on an up carbon, which makes the tert-butyl up on a down carbon.
Okay.
Now flip it and make the
So,
ethyl
I could have
up
put
on
the
a down carbon.
butyl here.
You could have.
Okay, that's what was confusing me because I was like, I don't know how to tell which one. But as long if I put this on a down carbon, then I have to keep that constant.
Good.
So
Exactly.
Now it's gonna be on an up carbon.
And now this is 1,4, so it really doesn't matter whether you go clockwise or counterclockwise, they're always opposite each other. So like here I was talking about clockwise and counterclockwise. Here it matters less because they're just directly across. Exactly. It is. It is. Yep. Sorry. Yeah, it is. But I would make more clear that this is axial by having it straight up instead of a little bit crooked.
Yeah.
And maybe make. That's okay. One thing that can help is by drawing in the hydrogen on those carbons to really demonstrate this must be axial because this is more equatorial.
Is that just, is the solution just poorly worded? Because I thought hydrogens don't have steric strength.
Right, it's the hydrogens of the methyl groups that are interacting with each other. So if, like taking this example, when I clink these groups together because they're fighting for space, what's actually hitting? The hydrogens are hitting. Hydrogens themselves don't fight for space. But these on these bigger groups, it's kind of hard to say. Can I keep this? Okay, you're welcome. See you guys tomorrow.
So, like, we're confused how the, like, flips happen because I'm thinking they happen, like this or like that.
No, they. Do you want to feel it? What I like to do is take two groups that are 1,3 to each other. I'm going to do this on the camera. Two groups that are 1,3 to each other, take them from up to down, and then take the groups that are next to them and take them from down to up. And that's how all of the carbons flip. So when I take these that are 1,3 to each other and I flip them, the one that's in between them starts moving. And then I take the next 1,3 and I flip them, the one that's in between them starts moving. So if you're going to do this at home and practice with a model kit, take a 1,3 pair and flip them from up to down. Take a 1,3 pair and flip them from down to up.
So I'm wrong then. So these
We're not flipping the molecule over, we're flipping the chair by going through a boat.
These two should be on the bottom, and this one should be on the top.
Your orientation, I think, is okay, but you have a up, up, up group. You drew them as down, down, down. Are those not dashes?
No, these are my wedges.
Oh,
Sorry.
Is this?
They're, like, connected.
yeah, up, up, up. And then you have
These are up.
Yeah, but they're on up carbons.
That's what I'm confused about.
So they're not
supposed
up.
to be on down carbons.
Yeah, so why aren't they?
So they should be down here.
They should be on, sure. You could rotate in multiple directions. So you guys,
They just have to be on a down carbon.
that's right. It doesn't matter which down carbon you choose. They have to go on a down carbon.
And then they gotta
Take care,
go
Patrick.
axial.
Bye, Jacob.
Or equatorial.
Good. Yeah, so if you notice that their carbon hasn't changed, they're still on an up carbon, or if you notice that they haven't flipped from axial to equatorial, then you've probably gone on the wrong position. I think part of the challenge with this is how much freedom there is.
Yeah, because there's no right and wrong.
Exactly. Well, there is.
Well, I guess there is right and wrong, but.
There is right and wrong, but there's multiple correct answers.
That's
And
What? No, that's great. Then you have more chances to get it right.
right.
But then you have, I don't know.
But then it can be harder to interpret.
Because I was like, that was the different thing that he had.
But then both together.
But they were, as long as they're all down. Did you know about that little summary thing that I posted on Canvas, John?
No.
Did you see that?
On a discussion board or something?
Yeah.
No.